Here's a second video on how to do the online air track collision lab. Last one I did trial one and for Elastic and Inelastic and put all the numbers in there as I went. This one's going to be a little bit more streamlined. All the numbers will already be there. So for this lab, if you haven't looked at the other video, all of the instructions are down here. I'm not going to read them all to you because you can read those. I would just click on this link and that'll open up a simulation that looks like this. An air track is basically just an air hockey table in a straight line that has some cars on it. The part that most people tend to have issues with is how to fill out their data table. When you're doing this lab, don't forget there are pre-lab questions. We're going to come back to this picture in a little bit on the third page, and then our data tables start on page 4. You'll notice that all of my data is already in here. I'm just going to show you where it came from and save the time of watching how I typed it in. Alright, so first things first, when we go to this lab, we want to make sure we get the masses, the lengths, and the times. That's the data that we're going to be getting from the simulation. So we're going to get both M1 and M2, L1 and L2, and all the times. Time 1 initial, time 1 final, time 2 final, and same thing down here. M1, M2, L1, L2, time 1 initial, and time 1 and 2 final. That's the information we're going to be getting from our sim. How do we do that? First, to get the mass, I would say, okay, cart 1 goes on there. I get 1,069. You'll notice that's what I have here for M1, both Inelastic and Elastic, 1,069. To get cart 2, I just do the exact same thing. I just plop it on there. I get 1,408, and that's what I get for mass 2 for both. To get the length, very easy to do. Open up the little length thing. I click and drag my ruler. Here I've got about 11 and what was it, about 11 and a half, I think it was. Oh, 12 and a half, I'm sorry. 12 and a half and a little more than that, maybe 12.6, 12.7, and that's what I wrote in here. L1 is about 12 and a half, L2 is just a little bit longer, about 12.6, and I get that for Elastic and Inelastic. Now I actually have to do the lab. You have to make sure you turn the air on. I make it go. Cart 2 went to the left, cart 1 hit and bounced back. That's going to be very important a little bit later, and I purposely wanted to show you that because it can mess with your numbers if you're not paying attention. Now this brings us back to the picture that I mentioned on page 3, because we have a time 1 initial, time 1 final, time 2 final. Which one is which? Because I have a bunch of different times here. I've got a time over here, I got 2 times on the right. Which one goes where? Well, you can see our picture. Time 1 initial is the time that exists over here on the right side, the top one. Time 2 final is the left side, top one. And time 1 final is either over here or over here. Now why is that? Well, time 1 initial is this guy because it's when cart 1 goes through this photo gate on this side before the collision. After the collision, it hits cart 2 goes off in this direction, so cart 2 is the first one to go through here, and the final means after the collision, so that's why it's the first time over here on the left. Now cart 1 can hit and bounce back like we saw, so its second time, its final time is going to be over here. Or it can hit and keep going after cart 2, so its final time would be on this left side. In this particular case, it hit and bounced back, so it's going to be over here. So those are the times that I plugged in for time 1 initial, time 1 final, and time 2 final. You see time 1 initial, 0.1077 is the time right here. 0.1258 is right here, time 2 final. And time 1 final is on that right side, the bottom number, 0.7861, 0.7861. Now what we're going to do is we're going to finish getting our data for the Inelastic. M1 is the same as long as we don't hit a new experiment. M2 is the same, L1 is the same, L2 is the same, and you'll see when we run it, T1 is initial is going to be the same as well, 0.1077. So here we go. How do we do that? I got to bring my plunger back. It's got my spring-loaded cart shooter. Turn the air back on. I am going to change to Inelastic collision, make it go, there it goes. Alright, and you can see 0.1077 is still my initial time. How do I get T1 and 2 final? How do I get this 0.502? I did that by adding up these 2 times together because both the carts went through together. And that's how I got T1 and 2 final. Everything else is stuff that we're going to calculate. If you're not sure where I'm getting some of these equations when I talk about them, they're after the questions. They're all down here, and you can follow along looking at that if you'd like, or just follow along with the video and do the stuff as I'm doing it. All right, V1 initial is length 1 divided by time 1 initial. And when I divide those two, I get the 116.06. V2 initial is always 0 because car 2 is not moving before the collision. V1 final is L1 divided by T1 final. Now you might notice there's a negative here. When our car, when we were doing elastic, it hit and bounced backwards. We're going to say that's in the negative direction. So my velocity after the collision would be negative. That matters. Make sure if it bounces backwards, you got to make it negative. V2 final is L2 divided by T2 final. When I divide those numbers, I get the 100.159. For inelastic collision, V1 initial is L1 divided by T1 initial. V2 initial is 0, just like it was with elastic because it's not moving. V1 N2 final is the speed of both car 1 and 2 because in inelastic they stuck together. And that's going to be length 1 and 2 added together. In this case, that would be 25.1 divided by T1 and 2 final. And when I divide those two numbers, I got 50. Now down here, how do I solve for momentum? P1 initial, momentum of car 1 initially. I'm going to scroll up because I'm going to get my numbers for blue stuff, elastic, from blue stuff, elastic collision. P1 is mass times velocity. And since it's P1 initial, I want mass of car 1 times the velocity of car 1 initial. I multiply those two together, I get P1 initial. P2 initial is 0 because the car 2 is not moving before the collision. Total momentum, total P initial, is these two numbers added up, which is very easy since this one is 0. So it's basically just what P1 initial is. P1 final is mass of car 1 multiplied by the velocity of car 1 final. And notice the negative is here. That's why my momentum is negative, because momentum has a direction. P2 final is mass 2 multiplied by V2 final. Total momentum after the collision final is these two numbers added up. Add the two together and you get total final momentum. Change in momentum is total P final minus total P initial. That's how I got that number. And then your percent change is actually the equation's written right here. I take my change in momentum, divide it by total P initial, and I multiply by 100% to get my percent change. And that should be a very small number because momentum is supposed to be conserved. It shouldn't be more than 1, 2, 3%. I got very, very low percentages here, but sometimes you'll get 1 or 2 or 3, and that's still okay. You don't want to see much higher than that. Now, if you see higher than that, you might have made a mistake. All right, for inelastic, P1 initial is still mass 1 times velocity 1 initial, and that's 124,071.49. P2 initial, it's still not moving before the collision, so it's still 0. Total initial momentum is these two numbers added up, which is still just equal to P1 initial. P1 final is mass 1 multiplied by V1 and 2 final. Since they're moving at the same speed, it's the same for each. So P1 final is mass 1 times velocity final. P2 final is mass 2 multiplied by V1 and 2 final. Total final momentum is these two numbers, P1 final and P2 final, added up. Change in momentum is total final momentum minus total initial momentum. And then I do my percent change, that's delta P divided by total P initial times 100%. And that got me a 0.18% change. Now we're going to finish up with kinetic energy. Kinetic energy 1 is, now the equation for kinetic energy is 1/2 mv squared. So I'm going to use 1/2 times m1 v1 initial squared. If you didn't convert to grams and to meters, which most people did not, which is why I did not in here either, you're going to get very, very large numbers. That's okay, because we have grams and centimeters instead of kilograms and meters. Kinetic energy 2 initial is 0 because it's got no velocity before the collision. Total kinetic energy is these two numbers added up, so it would just be equal to kinetic energy 1 initial. Kinetic energy 1 final. It's 1/2 mv squared again. What m's and what v's do I use? For kinetic energy final, for 1, I'm going to use 1/2 m1 times v1 final squared. Because it's squared, the negative goes away. There's no negative in kinetic energy. Kinetic energy 2 final is 1/2 m2 times v2 final squared. Total kinetic energy final are these two numbers added together. Change in kinetic energy is total kinetic energy final minus total kinetic energy initial, and that should also be a very small number because kinetic energy should be conserved in an elastic collision. For the inelastic collisions, kinetic energy 1 is going to be the same as it was in the elastic because it's 1/2 m1 v1 final squared, and those are v1 initial squared, I'm sorry. So I would just have 1/2 m1 v1 initial squared. Kinetic energy 2 is still 0. Total kinetic energy is these two numbers added up. Kinetic energy 1 final is 1/2 m1 times v1 final squared. Kinetic energy 2 final is m2, 1/2 m2 times v final squared. The total kinetic energy is these two numbers added together. The change in kinetic energy is total final minus total initial. You can see it lost a lot of energy. It actually lost 57% of its energy. And that should happen. You should lose energy in inelastic collisions because the energy is not conserved in that type of collision. After that, you're going to go to some post-lab questions. Was momentum conserved? If it was a change of 0.1 or 1%, 2%, you can say, for all intents and purposes, it was pretty much conserved because there could be friction, there could be a few other things that would cause momentum to leave the system. That it's not a completely closed and isolated system, air resistance, things like that. Was energy conserved? Again, if it's close to 0, yes it was in your change. If it was not close to 0, like 57, not close to 0%, it would not be conserved. Why is energy not conserved in inelastic collisions? Where does the energy go? Well, check out the notes and you'll see where some of the energy might go if you look at that or on my webpage. And then you just want to keep answering all the questions 4, 5, and 6. Like, why do we need to put a negative in front of the measurement for either T1 final or for your velocity? That's because it goes in the opposite direction. And would our answers change if it was negative? Absolutely. Number 5, suppose the entire population of Earth gathered in one spot and were to jump at the exact same time. While all the people are in the air, would the Earth gain momentum in the opposite direction? That's kind of a fun question. I'm going to leave that to you to answer, and I'll go over that when everybody's finished with this lab. And similarly, when we all hit the ground a second or so later, do we knock the Earth out of its orbit? That'd be kind of cool if we could. So let's assume that everybody's all in Omaha, Nebraska, and we all jump at the same time. What would happen? And using conservation of momentum, we can figure that out. So hopefully that helped answer all of your questions that you have about how to get all your values for this data table. And if you have any questions, as always, just let me know.